Hello everyone, welcome back to our channel. So in previous video, we talked about the design about a key value store, especially how DynamoDB works in a distributed environment, right? Which means if we have multiple machines in a distributed environment, how the machines are going to collaborate with each other to replicate the data, to achieve high availability and also keep the data consistent, right? So now, yes, we talked about how different machines handle the data by collaborating with other machines, for example, in a consistent hash manner, right? So now in this video, we are going to into more details about how a single machine, how a single node in a distributed environment store the key value, right? So to be more specific, we will design key value database on a single node. Okay, cool. So that's why the title of this video is key value store design on a single node. Okay, cool. So let's see. We are designing a in-memory database, in-memory key value store, right? So how do we do that on a single machine? That is very simple, right? So we just use a hash map in the memory to store the data, right? So let's see, we have a request, which is key. Let's see, the key is a string, which is this string, okay? And also the value is, let's say, 67, okay? So now the request comes to our machine. Okay, so our machine will just store the data in a hash map, right? So we have a in-memory hash map. So, and we just insert this key and value into the hash map, right? So now we have this string as key, okay? And also the value of this is 67. Okay, so we have this hash map, okay, and maybe we have some other keys, which is like, let's say, random string, and also the value is even a different type. Let's say it's a JSON string, right? So it's like this. Okay, cool. So this is a in-memory hash map, right? So, and later when a read request came, so let's say the read request reads the key of this key, right? So then it checked the in-memory hash map. It say, oh, I have the key in memory, and it just returns this value, which is a JSON string, right? So this is how it works if we are designing a key value store or an in-memory key value store, right? So which has no problem and it's simple. However, there could be problems of in-memory storage because let's say the single machine dies, right? Then the memory data is lost. So we don't persist the data, right? So we want, let's say now we are going to design a persistent database, persistent key value database, which means we must store the data not only in memory, but we should store it on disks or SSDs, right? So that's how it works. So now let's say how can we design such a key value store in memory, in disk, right? So now we are going to design a key value store or key value database which stores data on disks. Okay, so we can persist the data forever, right? Okay, so the most naive way we can do this could be like this, right? So let's say our table name is, the table name of the data we are going to store is, let's say, employee table or something like this, right? So then we can just create a directory or a folder on the disk which is named employee table, right? So it could be something like this. So we could have a directory, and the directory name is called employee table. Okay, and then let's say we have a request, which is I want to store key as, let's say, Ken. Okay, and the value is, let's say it's the key, let's say it's some ID. Okay, let's say it's ID like this. This is ID, and the value is a JSON string. So it's something like, oh, I have the name, employee name, which is Ken. I have the age, which is, let's say, 28. Okay, so and also you can also store any other information about the employee in the value. Okay, so now let's say this request comes, and now we need to store this data on disk. How can we store it? So now we know, okay, I want to store this data in the employee table, right? So we go to the directory of the employee table, and we just create a new file, which is named the ID of this key. Okay, so we create a file here, and the file name is this key. Okay, so the file name is this key. Okay, and let's say we have some other request to store a key value. Then we create a new file which is named after the key. Okay, so let's say we have another key which is like this. Okay, cool. So now when a read request comes, okay, then we check the directory to see, okay, whether the directory or whether the folder contains a file whose name is the same with the given key. If there is such a file, then we read the file and we return the content of the file to the client, right? And if there is no such file whose name is the same with a given key in the read request, then it means, oh, we don't find this key value, so we return empty or null string to the client, right? So this is how it works in a naive way to do this, right? And also to accelerate the to make it run faster, or to make the read more faster, we can also have some cache in the memory, right? Okay, so we can, so this is disk. Okay, so let's say this is disks. Okay, and we also have the in-memory data, and this is the memory. So in the memory, we can also have the same hash map, right? So we can use hash map to store recently queried data. So let's say in last request, we get the key, this, and from the disk data, we return this value, right? And now we store this data into the hash map in memory, right? So later, when another request comes to request the same keys data, then we don't need to query the disks anymore, right? So we just return the data from the memory. So this is an optimization to do this, right? So let's say, okay, so this is how it works in a simple way, right? And what problem could this have? Okay, so there could be two problems, right? First, we are storing the data on disks, right? And we are storing each key as a file. Let's say we are on a single machine. Let's say we could save 500 million keys and values. That means in this employee table folder, we are going to store 500 million files, right? Which is a lot. And when you have more files, your system performance will be lower than before when you do those queries, right? And another thing, this is the first problem, right? So first problem, too many files in system, okay? And also we have a second problem, which is random read and write. What does this mean? So this means, let's say, Okay, so we have other files here. Okay, so we have maybe millions of other files, right? So we have so many other files in the same directory. Okay. Cool. Now let's say in the first read request, we read the data from this file, from this key, right? Okay, so the disk will read the data from here. Okay, and then next read request, let's say it reads data from this key. So we are going to, the disk will rotate and position its head to this file's position. So this position could be very far away from this file's position, right? So they are very far away from each other on the disk. So in this case, it's a random read, right? So we are jumping the head of the disk to another different location on the disk, right? And then maybe for a third request, it's going to request the data in this file. Then the head of the disk is going to jump to this position, right? So if you understand the characteristics of a hard disk usually when you write and read data, the performance is best if you are going to read and write the data in a continuous way, which means on the disk, if you are, so let's say here, okay, so let's draw this. So let's say this is a disk, okay? So this is a disk, okay? Let's say the file, the first key is in this position, the second key is in this position, the third key is in this position, so they are continuous, right? They are adjacent to each other, okay? Okay, cool. So let's say we read the data continuously, which means, okay, the first key is this file. Okay, so if we read the first key, it's this, it hits this file, and then the second key hits this file, and then the third key hits this file. Then you can see the three files are adjacent to each other. They are continuously laid out on the disk, right? So then the performance will be the best. So it's very fast because the disk will just seek the data from this position to this position and then go to this position. So you can see it seek the data on the disk continuously, right? So with this manner, the disk read and write have the best performance, okay? So however, there's no guarantee in a key value store we are going to read and write the keys data continuously, right? So for example, our first read request should hit the first file, okay? But the second key could be in this location, okay? So which means, okay, so the disk seek the data from the first file, and in order to get the second key's data, it has to jump far away to another location, right? And now let's say the third key's data is in this file. So then that means, oh, I have to jump back to this file, which is also far away, right? So with this, you can see the performance will be bad for a hard disk to read and write, right? So this is called random read and write. So which is our second problem. And the random read and write has a bad performance, okay? Which means it will read and write data very slow. Okay, so how can we resolve this problem, okay? So now we are going to talk about a very typical and a very famous algorithm. Not algorithm, but maybe some design, okay? So it's called LSM, which is log structured merge tree. Okay, so what is this? Okay, so if you are interested in this, actually the design we are going to talk about here is actually from the Cassandra database. Okay, so it's a database designed by Facebook at first. okay? And you can go to this link to read more details about what's the architecture of Cassandra database and how it handles the read and write of key values in a log structured merge tree way. Okay, so now let's go and talk about how we design a key value store with log structured merge tree on a single node. Okay, cool. So with LSM, we have two concepts, okay? One is the MemTable, and the other one is called SSTable, okay? So what are they? So let's talk about how it works. So first, let's talk about the write path, okay? Write path. How do we write a key value into the storage, okay, on a single node? Cool. Okay, so now let's say we have a request which comes, okay? So let's say we are still storing the same data, which is key value, okay? Cool. Let's write it here, okay? So this is the request which store this key and value. Okay, first, okay, so this request comes to our machine, okay? So first, we have a log file. So we are going to write this key and value into a log file. So what is a log file? Log file, okay, this is a log file. Okay, log file on disk, okay? So first, we are going to write this data into the log file. Log file is just a normal file, right? So when this new request comes, we are just going to store this and append this key and value content into the end of the log file. So let's say in the log file, we have the previous data, okay? So this is the previous data we have written to the disk in the log file, okay? So you can see here, it's continuous write, right? So now let's see for this request, it comes, this is the latest request, right? We are just going to append this data into the end of the log file, okay? So this one, this data, let's use a different color. So this is data stores the key and value of this request. So this is called log file, right? Okay, so we started here first, okay? So this is the first step. We store the data on the log file, and second, we also have the in memory, okay? So let's draw a line here, okay? Okay, this is a line. So above this line, it's in memory data, and below this line, it's disk data. Okay, so we talked about that. Okay, now the first step is to store the data, append the data in the log file, right? And now the second step is to store the data in a MemTable. What is a MemTable? You can think a MemTable is just some kind of hash map, okay? It's some kind of hash map in memory, okay? So it's just the same thing we talked before, okay? So now we are going to store the key and the value into the in-memory hash map. And after the second step, which is written the data to the hash map in memory, then we respond back, okay? So then we respond to the client to say, okay, your written request is successful, okay? So this is how it works. Okay, now let's see why this is for the write path, okay, why it has a high performance. So first, we are writing the key and value into the log file on disk. And you can see for every request, new request, we just append the data into the end of the file on disk, right? And with the appending operation, it's not random write, right? So we continuously write the data to the end of the file. So it's a continuous write for data on disk, right? As we talked before, when you continuously write the data on disk, it has a best performance, right? So we have the best performance here. And then we write the data into memory, and memory operation is even faster, right? So that's how the write path is very fast, right? So cool. And now you will ask, okay, what's the functionality of this disk file, of this log file, right? The log file's functionality is to prevent data loss on machine crash, right? Let's say you don't have this log file and you just write the data to memory. And if the machine crashes, machine dies somehow, then you lost the data, right? Because your data was in memory and it was not persisted on disk. So with this log file on disk, what you can do is that, okay, the data machine crashes, and then the machine crashes, and when the machine comes back, you can see, oh, I have a log file on disk. Then you can replay this file. Replay means you read this file and reconstruct the in-memory hash map, right? So with this, you rebuild the hash map, so there would be no data loss, right? So that's the functionality of the log file, right? So this is a write path, right? Okay, and so we talked about on a request path how the write request is performed, right? So now let's talk about how we are going to persist this data on disk, the in-memory data on disk, okay? Yes, we talked about we have the log file, but the functionality of this log file, as we said, it's to prevent data crashes, right? It's not mainly used as the main storage of the key values, right? And also another thing you have to notice is that we have limited memory, right? So let's say after you save 1 million or 100 millions of data in memory, then you are out of memory, right? So you cannot write more data to log file and to the hash map anymore, right? Even though you have enough space on disk, right? So you cannot write the data anymore. So for write, with only log file and the in-memory hash map, it's not enough. We have to find a way to persist the in-memory data, or the data in both the log file and the memory hash map, to the disk once the memory is run out, okay? So how do we do that? Okay, the way we are going to do it is called a flush operation, okay? Flush the MemTable to SSTable, okay? So MemTable is a hash map we talked about here, and SSTable is the table, is a file which is going to be stored on disk from this hash map in memory, from this MemTable. Okay, so how we do it? So basically, from high level, it means, okay, once we run out of memory, we just flush the data from this MemTable to a new file on disk, which is called so it's a new file which is called SSTable, okay? SSTable, okay? So we flush the data, we write the data from this MemTable to this SSTable, okay? And how we are going to write it? I mean, we have many data in this memory, right? How we are going to write the data into this SSTable? Okay, so the simplest thing to do is you just get the first key in this hash map, and then you get the next key in the hash map and write the data sequentially to this SSTable, right? However, the problem is that the key is not going to be continuous, right? So, I mean, the first, for example, let's say you have your key is like, in the hash map, the key is in this sequence, it's like 98 and 60, 30, 120, 150, 200, 128, 128. Okay, so this is a key in your. So when you write the key and the data from this MemTable to the SSTable, you are going to store the key 98 data first, and then you are going to store 60. You are going to store 30, right? So you are writing this in this sequence to the SSTable. SSTable is just a file, okay? There's no problem usually with this. However, with Cassandra or even some other database, let's say we have a requirement, which is we want to query the keys in a given range, okay? So let's say we want to query the data whose key are between 60 and 90, okay? So in that case, if we randomly store the key on the SSTable or even in the memory, we will have no way to do this kind of range request in a performant way, right? Because they are randomly stored, so you have to scan all the data in your hash map and in your disk to get the data whose key are between 60 and 90, right? So if we want to do this in a performant way, usually we need to store the data by their keys in sequentially, right? So in this case, we want to store the data with this order. So with 30 from the smallest to the largest, right? It could be 30, 60, 98, and something like this. So it's sorted. We want to store the data in both the memory and the SSTable in a sorted way, right? So this is, with this, in the future when we do a range request, we can quickly find the data in a given range without querying or scanning all the data in the table, right? Okay, so how do we store the data sequentially? Okay, so that depends on the in-memory data. So for the in-memory data, instead of using a hash map, we can use a sorted tree, okay? Sorted tree to store the data. So for example, we could use a binary search tree, or we could use a B tree to store the data in the memory, right? Which means the data, the keys are sorted, right? So I'm not going to talk about how binary tree works and a sorted tree works. That's the basic data structure you could read from any book or from any YouTube videos, right? So, but the point is that with a sorted tree or with like binary search tree or B tree, so you can quickly search the data in a given range, right? So, and also the keys are sorted, are stored in a sorted way, right? Because the keys are stored in a sorted way, when you flush the data from the MemTable to the SSTable, you can flush the data from the smallest key to the largest key in a sorted manner, right? So that means even in this SSTable file, the data is stored from the smallest key to the largest key, right? So here in the SSTable, it's stored like this. So the first entry in this table, in this file, in this SSTable file is, key 67, value something, okay? And the next key is 78, and its value is something. And the next key is 180 and 90, okay? And then the value is something. It's sorted by keys in this SSTable file, right? Okay, cool. And cool. So we talked about flushing the data from the MemTable which is in memory, to the disk onto a SSTable file, right? Okay, now after we flash the data to SSTable, it means, oh, your data is indeed persisted on disk, which means it will never be lost again, right? So then we can clear this log file. Okay, so we can clear this log file, so which means we delete the log file from disk, and also we clear this memory. Okay, cool. So the memory and the disk log data is cleared. Remember, the reason why we do this flush is because we don't have enough memory, right? So now we clear the memory and also we clear the log file. Okay, so now let's see when a new request comes, a new write request comes to our machine. Now we are going to create a new log file. Okay, and we are going to write this data at the beginning of this log file into this newly created log file. And also in the second step, we're also going to initialize a new in-memory, a new MemTable. And also similarly with this MemTable is also a sorted tree, right? It's a B tree or it's a binary search tree which store the data. Okay, so it's a in-memory tree to store data in order of keys. Okay, cool. And now we are going to do the same thing again. So let's say in future you have more write requests. So then we append the data to the end of the log file continuously, and then we write the data to the in-memory table, the MemTable continuously. And once the memory is out of memory, so achieved our max memory, then you flash the MemTable to a new SSTable. Okay, so let's say you stored it into a new SS. Let's call this SSTable 1, SSTable 2, and the previously SSTable is called SSTable 1. Okay, and in this SSTable 2, you store the new data. Okay, so let's say we stored 56, some value, and also we stored key 78, and also we stored key 280. Okay, some value. Okay, and then you clear this log file again, and you clear this MemTable, and we repeatedly do this. So with this, you can see at the same time we could have a single log file, a single MemTable, and all, but we could have multiple SSTables because SSTable is just a replication of the in-memory table, the MemTable at some point, right? So whenever you flash this MemTable to disk, we will have a new SSTable, right? And you can notice that in different SSTables, we could have the same keys, right? So for example, before we flash the MemTable 1, so let's say it could have a key, which is 78, right? So we flashed this data to SSTable 1. And then after we cleared the MemTable 1 and the log file 1, we created a new log file, right? And also we created a new MemTable 2, right? And in the MemTable 2, we can have a request which comes into the machine to say, oh, now I want to update the value of the key 78, right? So then we update the MemTable with the key 78 and its latest value. And once the MemTable 2 is full again, then we flash it to a new SSTable 2, right? And here, because there is key 78 in the MemTable, so now key 78 will be stored into SSTable 2 with its latest value, right? So with this, you can see in different SSTables, you could have the same keys. It's just one of the keys, one of the file will have the latest data with the latest written data, right? Okay, so this is a write path. Okay, now with this, let's talk about how the read path works. Okay, cool. So we will talk about the read path in the next video. So see you in next video. And thank you for watching this write path of this log structured merge tree key value store. Thank you. See you next time.